This is the Tachyon Paradox, one of the most baffling ideas in all of physics. And it's all because of this weird particle called the tachyon. Tachyons are hypothetical particles that always move faster than light. If they exist, they'd be the first thing to break Einstein's theory of relativity. But if they don't exist, we have to explain why we see certain astronomical phenomena. So tachyons may not exist, but their potential discovery would be pretty huge. There's just one problem, though. Faster than light travel means that effects can happen before causes. That breaks causality, and by causality, I mean the simple idea that cause must come before effect. Like if I want to make an omelet, I need to get the ingredients out before I crack the eggs. And if I want to go back in time and stop Thanos from killing my dad, I'm gonna need to get there before he snaps his fingers. Things are generally considered to be caused by things that came before them. It's just how things work. So while faster than light travel has been hypothesized for a long time, once we actually see evidence of it, it could turn our entire understanding of reality on its head. First off, let's talk about what we know about faster than light travel. Light moves at exactly 300,000 kilometers per second in a vacuum. That's the fastest speed anything can move. At least that's what Einstein told us. According to his theories, space and time intertwined in a flexible fabric known as spacetime are entirely relative depending on your frame of reference. This also means that time is relative. Time passes differently for someone moving really fast versus someone who's still. In fact, the faster you move, the slower time goes for you relative to someone who's still. This is called time dilation. If you were to shoot off in a spaceship at 99% the speed of light and then immediately turn around and come back, you'd find that less time had passed for you than for everyone you left behind on Earth. The closer you get to the speed of light, the more pronounced this effect becomes. And theoretically, if you could somehow move exactly at the speed of light, time would completely stop for you. But this is where tachyons come in, because according to math, if you take something with mass and accelerate it to the speed of light, it would take infinite energy. And that's not physically possible, so scientists hypothesize that there might be particles out there that do and have mass and therefore can travel faster than light. These hypothetical particles are called tachyons. We don't know if they exist or not, but we have some reason to think they might. There are some astronomical phenomena that seem to defy the speed of light limit, like quasars that are found at distances so great that the light from them would take millions of years to reach Earth, but they also appear to be changing over time. This implies that something is happening over there that is influencing what we see here. And if that's true, then something is communicating faster than the speed of light. Also, there is a type of radiation called Cherenkov radiation that is emitted when charged particles move through a medium faster than the speed of light. That's right, faster than the speed of light. And it's been observed here on Earth. Maybe those particles are tachyons. Now, there's also evidence that neutrinos could be traveling faster than the speed of light, which is pretty wild considering neutrinos are one of the most well-studied particles in the universe. But these are just correlations. We haven't actually observed a neutrino traveling faster than light yet. And the data is still being analyzed. But even if we did observe a particle traveling faster than light, it still wouldn't prove that tachyons exist. You see, there's another possible explanation for faster-than-light phenomena. That's because Einstein's theories also tell us that negative masses should exist, too. These hypothetical negative mass particles would sort of be like antimatter, only instead of every other property being opposite, their mass would just be opposite. While regular matter has positive mass, negative mass would repel normal matter, and it would also repel negative mass, meaning it would move away from everything else in the universe. If something had a negative mass, it would accelerate faster, and eventually it would be moving faster than light. So negative mass could explain faster than light phenomena without breaking Einstein's theories. And if this is the case, it could also explain dark energy. In fact, scientists believe that dark energy and negative masses may be related. Dark energy is a hypothetical force that is causing the expansion of the universe to speed up. It makes up around 70% of all the energy in the universe, but we don't know what it is. One hypothesis is that dark energy is actually a kind of negative mass that is causing the accelerated expansion of the universe. One way we might be able to distinguish between dark energy and negative mass is by looking at distant supernovae. Supernovae are exploding stars that give off a huge burst of light before going out like a candle. If dark energy exists, it would affect supernovae in a particular way. Basically, if it exists, it would make supernovae look dimmer than they should be. Scientists have looked at supernovae and found that they do seem to be dimmer than expected. And if this is true, then maybe that's evidence for dark energy, meaning negative masses could be real. But regardless of whether or not negative masses exist, if we ever observe a particle moving faster than light, it'll be evidence that something is going wrong with our understanding of physics. You see, Einstein's theories assume that nothing can travel faster than light, including information. Information is just another way of saying causation. If you hit a ball, the information that you hit the ball travels through the air faster than the ball itself. It's encoded in the motion of the ball after you hit it. In other words, the effect of you hitting the ball is caused by you hitting the ball. Cause must come before effect. But if we ever observe a particle moving faster than light, it would mean that effects could happen before causes. That would break physics as we understand it. Physicists have actually thought about this quite a bit, and they've come up with a few different resolutions. The most popular one is that faster-than-light particles could be a type of quantum foam. Quantum foam is basically a type of noise that comes from quantum fluctuations in space. Space is constantly fluctuating, creating these tiny little ripples. It's just the nature of quantum mechanics. These fluctuations could potentially be so small that we couldn't detect them. Or if they are larger, they could create faster-than-light particles. So it's possible that all faster-than-light phenomena are really just due to quantum fluctuations. Another solution is that faster-than-light particles could be some kind of illusion. Maybe they're not actually moving faster than light, but they re-interacting with our universe in such a strange way that it appears to us as though they are. A third solution is that our observations aren't wrong. Things do happen faster than light sometimes. Instead of abandoning Einstein's theories, we could accept that faster-than-light communication happens under very special circumstances. This could potentially solve a lot of problems in physics, but it would also change our entire understanding of the universe. Faster-than-light communication could potentially make things like time travel possible. If you could send information faster than light, you could send it back in time. This isn't as easy as it sounds, though. You can't just send information back in time. You'd have to send it to the future. Then you'd have to figure out how to bend spacetime in such a way that the information ends up coming back to you in the past. You see, sending information to the future is relatively straightforward. If you move really fast, time slows down for you. So if you moved fast enough, you'd essentially be traveling to the future. And since nothing can travel faster than light, you'd have to move at the speed of light. But as I mentioned earlier, it takes infinite energy to accelerate something with mass to the speed of light. So that's not really practical. Sending information back in time would be much more difficult. To do that, you'd have to move faster than light, which isn't possible. Or you'd have to change our understanding of physics. Now, while the idea of time travel is pretty exciting, it's probably better that we don't mess with it too much. Time travel has a lot of paradoxes attached to it. You know, the classic one where you go back in time and kill your dad, thus preventing your own birth, thus preventing yourself from going back in time to kill your dad. It's fun to think about, but it could actually break the universe. Of course, physicists are thinking about this too. They've thought up solutions to many of these paradoxes, like the Novikov self-consistency principle. This principle states that the universe will always be consistent with itself. So, if you went back in time and killed your father, you wouldn't actually kill your father. Something would prevent you from doing it. Maybe you'd try to kill him, but your gun would jam or he'd duck behind a rock or something. It's kind of a weird concept to wrap your mind around, but the Novikov self-consistency principle basically says that you can't change the past. And there are similar principles for changing the future. You can't change the future either. So any attempt to change things in the past or future would ultimately fail. However, all of this is hypothetical. We haven't actually observed faster than light particles yet. All we know is that there are some astronomical phenomena that seem to violate the speed of light limit. So while we don't actually have any evidence that tachyons exist, we also don't have evidence against them. If we ever do observe a particle moving faster than light, it could change our entire understanding of the universe. It could mean that space and time aren't relative. It could mean that the universe is full of negative masses. It could mean that our observations are wrong. There are a lot of possibilities. What do you think? Let me know in the comments below. And don't forget to subscribe for more videos.